Okay, this week we'll be talking about more in depth on imaging pulse sequences, in particular gradient echo imaging, and we'll also talk about fast spin echo imaging, which is an imaging sequence that's in the family of echo train pulse sequences. Before we get into that, though, I want to discuss a little bit more about 2D imaging in general, the so-called sequential versus interleaved acquisition. So in this top figure, what I'm showing on the left is the acquisition order for a sequential acquisition. These blocks represent slices through some kind of sample or the human body, where each black line here represents one k-space line. So if you look at the inner loop here, we would do signal averaging first on the first k-space line. So if we had 4 averages, we would acquire this line 4 times. And then we would move to the next line here 4 times, do averaging, and next line, and so on until all the lines for this slice were acquired. Then we move to the outer acquisition loop, which is slice location, so that means we move to the next slice, acquire the first k-space line, average, and so on until we make it to the final slice. Now for interleaved acquisition, we do have a different ordering of the acquisition loops. So the first k-space line could be up here or it could be down here. So it would be acquired, and then averaging would be performed, well, for the next average, first slice location, inner loop. Then we would go to the next slice, gather that data k-space line, go to the next slice, gather that k-space line. Then we go to another slice location. Then we go to the next phase encoding or the next k-space line. Okay, and we go to the next slice, do any averaging on that line that we might need. Then we go to the next slice, do any averaging on that line that we may need. And then the outer loop again, we move to the next k-space line, which would be the third line, and so on until we acquire all of our lines. So you can see that the acquisition order is quite different between these two methods, and certain pulse sequences are more suited for sequential, and certain sequences are more suited for the interleaved type. And so gradient echo sequences are good candidates for sequential acquisition because they have a short TR, while sequences that need a longer TR are good candidates for interleaved acquisition, so that you can achieve a certain image contrast and signal to noise ratio. So we'll talk now about some gradient echo techniques. There really are just 2 flavors of gradient echo imaging, that being incoherent or spoiled, and coherent, in which the transverse magnetization is refocused. In this case, this is called fast imaging in the steady state, or FISP. Now I wanted to just show a table of the different acronyms, just to give you a feel for how many different acronyms can be made just for gradient echo sequences, not only in themselves but also between the vendors. So it's quite some people call it a zoo of pulse sequences. And if you want to learn more about these other types of sequences that we won't discuss too much, such as true FISP, this book, The Handbook of MRI Pulse Sequences, is a very good reference. And when talking about gradient echo, spoiling is a big topic, so I'd like to discuss that a little bit here. The spoiling in general means that you disperse the unwanted transverse magnetization at the end or the start of the pulse sequence. And what that means is, let's say you have a long, or if you have magnetization at the end of your sequence that you want to get rid of, then you would want to spoil it. And we can do that by one of three methods. We can do that by using a long TR. So we can just have, let's say, 1 second between our 90-degree pulses. Then the MRI signal would have decayed away. Again, this is gradient echo. So our MRI signal would have decayed away by the time the next TR happens. So that's kind of an automatic way to do spoiling. Now, alternatively, we could use unipolar gradients at the end of the sequence to spoil the transverse magnetization that is unwanted. Or we could change the phase of the RF pulse, which I'll show you here on the next slide. I'll talk a little bit about gradient spoiling as well. So spoiling by gradients is accomplished by inserting a gradient into the sequence either after the pulse sequence has finished and before the next TR, or before the start of the sequence but after what are called preparatory RF pulses. And this gradient, and the spoil gradient, is typically called a trapezoid if it has this shape, and it can be applied along either the X, Y, or Z direction or all directions. And how would we spoil by changing the phase of the RF pulses? First, the important thing here is to not confuse the phase of the RF pulse with the flip angle of the RF pulse. So here, what I'm showing by the red arrow is a flip angle of about 20 degrees. And for the first TR, the phase of the RF pulse resulted in the transverse magnetization pointing along this axis here, which is called the y-axis. But at the second TR, the phase of our RF pulse, remember, not the flip angle is the same, but the phase of the RF pulse has changed, so that the direction of the transverse magnetization has come off of the is now kind of in the XY plane. It's not directly on the y-axis. At the next TR, we have a different phase, and so on, and so on. And this series of events where the RF phase is changed is called phase cycling. And there is a specific equation. Usually the phase is changed as a quadratic function. So it's not just a random, the phases are not just randomized, but there's a specific equation which tells you, or can give you the optimal spoiling by this method. So we've discussed why gradient echo is fast before, but I want to go over this just real briefly again to remind you. Again, in gradient echo imaging, we usually apply a very short or small flip angle, and that results in just a small difference, just a small loss of longitudinal magnetization, but a relatively large increase in transverse magnetization. So if we compare these two, if we just pull them out, this little section is the loss here, and this section is the gain in transverse magnetization here. So clearly there is a big difference. So we can use a very short TR, because in between TRs, although we have a small flip angle, we're able to achieve a large amount of transverse magnetization relative to the amount of longitudinal magnetization that we've lost. And when talking about gradient echo sequences, it's important to talk about the so-called steady state. So just in general, steady state is just a state of dynamic equilibrium. So we'll just use this bucket of water analogy here. So if you have a bucket of water that's in a steady state, and let's say your bucket of water is leaking, then to be in a steady state you would need water going in at the same volume that it's flowing out. And so now of course we want to talk about the steady state in gradient echo imaging. So remember, in graded echo imaging, we only have one RF pulse. Usually the flip angle, we just call it theta, is less than 90 degrees. And before the first pulse, we have M0. And what I'm assuming here between these pulses is that the transverse magnetization completely decays away. So I'm only going to consider longitudinal magnetization. So if we consider MZ at point A, at point B, we have MZB equals MZA times cosine of theta, where theta is the flip angle. And from B to C, we have, of course, T1 relaxation. So MZ at C is given by this equation, which you've seen before. So at the steady state, to achieve the steady state, we want the situation where, again, these pulses just keep repeating, so just picture these as being repeated. We want the situation where MZ at some C down the line equals MZ at some A down the line here. Now, not necessarily the second and third pulse, but somewhere down here, this situation will be achieved, and that's the steady state. And since, again, we assumed that the transverse magnetization was gone, so this is a spoiled sequence because there is no transverse magnetization. It doesn't really matter right now how it was spoiled. We'll just call it spoiled. So this is the signal equation for this type of sequence. So this we can use to predict what the signal would be in certain tissues that have, excuse me, I'm trying to get my cursor back here, that have, so if you knew the T1 and the T2 star of the tissues, just by applying TR, TE, and a certain flip angle, you could predict what the tissue contrast would be. And that signal equation is maximized when this angle here is set to the so-called Ernst angle, which is given by this equation. Our angle whose cosine is e to the minus tr over t1. So if we go back to our steady state analogy, the bucket of water here, the water really is the longitudinal magnetization. So if the water level is going up and down, then we are not in a dynamic equilibrium state. And just as in the gradient echo situation, if our longitudinal magnetization throughout the sequence is not stable or is not steady, okay, we're not in a steady state. When the water going in is analogous to the T1 recovery, and the water coming out is analogous to the excitation pulse. So I want to show some more images of our famous kiwi fruit. These were taken by a sequence called fast low angle shot or flash, and these are T2 star and T1 weighted. And the first row here, they're T2 star weighted because the flip angle is very short, very low. The next row has a flip angle of 90 degrees, so they're more T1 weighted. And to get an appreciation of the difference in contrast between these two, I just subtracted this row of images from the first row of images to give these difference images. So these are just, these images were not, again, acquired by the machine. They're just processed. These are just subtraction images to show you the difference in contrast between the T2 star weighted images and the T1 weighted images. So you can see that there's something going on in the T2 star weighted image here. Since they're brighter, you lose that signal in the T1 weighted image. Okay, so let me go back here just to say something real quick about T2 star and T1 weighted imaging with regard to the flip angle. you can see that if we have a low flip angle like I'm showing here, the longitudinal magnetization does not change very much. So if we're not changing the longitudinal magnetization significantly, then we're going to restrict our T1. We're going to restrict the weighting of the image to something other than T1. Okay, to get a T1 weighted image, we really need to be changing the longitudinal magnetization significantly. And also, in order to get a T2 star or T2 weighted image, we need to be changing the transverse magnetization significantly. So here, we could say that we're more T2 star weighted than we are T1 weighted if we have a low flip angle. And remember, for gradient echo, we cannot be T2 weighted because we do not refocus. We do not refocus the magnetization, so our signal is always an FID. Okay, just a couple slides briefly to discuss some clinical applications of T2 star weighted imaging. They're commonly used, this type of imaging is commonly used for looking at hemorrhage in general. Hemorrhage is the products of hemorrhage, or if you have a large amount of bleeding in the brain or in other organs, you'll have a buildup of iron, which is paramagnetic, so it will dephase your signal. And that, since T2 star weighted imaging is sensitive to dephasing, you can have hemorrhaging will actually weight the T2 star weighted image ends up being sensitive to that hemorrhage. Another type of application is susceptibility weighted imaging, and this is another form of T2 star weighted imaging, but it adds some more information, such as the phase of the image, and this is useful for detection of stroke, epilepsy, brain tumor characterization. Perfusion weighted imaging is a very interesting type. It allows you to look at blood flow, for example, near tissue after a stroke, which is very important because clinicians want to know what regions of the brain still have blood flow after stroke, and that can help guide in prognosis. And also in Alzheimer's disease, another thing to do is to be able to tell what parts of the brain are still perfused with blood. And this can also be used in other organs as well. So that's all for this particular topic. And again, as the outline in this week's module indicates, please try to read through Hishemi chapters 19 and 20, I believe, are the ones that deal with gradient echo imaging.